When subjected to acid-catalyzed dehydration, will 4,5-dimethyl-2-hexanol or 4,5-dimethyl-3-hexanol yield 2,3-dimethyl-2-hexene as a major product? So to understand this question, in elimination of alcohols for acid-catalyzed dehydration, alcohol undergoes dehydration to form an alkene when heated with a strong acid. It is important to note, though, that in the order of stability of carbocations is tertiary as the greatest, then secondary, and then primary. This explains why the major product of a reaction depends on the stability of the carbocations, which is what we'll find out in solving this problem. We know that both secondary and tertiary alcohols follow an E1 mechanism. Both alcohols in this problem are secondary. Something tricky, though, about this question that we need to keep in mind is that during dehydration of secondary alcohols, the carbon skeleton can rearrange itself. You can initiate the reaction and get two products, both major and minor, which show you that they can rearrange how the carbons are connected. Let's start with 4,5-dimethyl-3-hexanol. In our first step, alcohol reacts with an acid, like H3O+, to form a protonated alcohol, also known as an oxonium ion. Here we see the oxygen being attracted to the proton in the H3O+. Then the oxygen gets protonated, and you have the protonated alcohol with a positive charge on the oxygen that it doesn't like. Step 2 involves the elimination of a water molecule to form a stable carbocation. We see that a secondary carbocation is formed, which we know that they do not like because they want to be tertiary. So here, in step 3, the carbocation changes from the less stable into a transition state, where the hydrogen moves in between the two carbons and starts stabilizing the positive charge. We can see this transition state where neither of them are secondary or tertiary, they are all kind of in between. Eventually, though, they'll end up coming from a less stable secondary to a more stable tertiary carbocation. This is called a 1,2 hydride shift. We are shifting a hydrogen to form a tertiary carbocation. Now we have a rearranged carbocation, where we have the option to either eliminate one of the hydrogens on each side of the positive charge. Here we see both products, major and minor. Most of the time you'll form a more stable alkene, which is the 2,3-dimethyl-2-hexene, and a less stable alkene, which is shown on the right. Our major product here has 11 alpha hydrogens, which proves to be more stable and is a Zaitsev product, which means it's the most substituted alkene. Our minor product has 6 alpha hydrogens, telling us that it is less stable, and a Hoffman product, which means it's the least substituted alkene. Here we have 4,5-dimethyl-2-hexanol. From the start, we see some similarities to 4,5-dimethyl-3-hexanol. One thing, though, that originally confused me here is rearranging its carbon skeleton like we did previously. Even though last time we went through a 1,2 hydride shift, in this instance, 4,5-dimethyl-2-hexanol would have to undergo 2 hydride shifts, which would make it a 1,3 hydride shift, to produce a more stable tertiary carbocation. In this case, it's not likely that it'll undergo 2 hydride shifts, even though we know that 2 consecutive 1,2 hydride shifts would ultimately result in a tertiary carbocation. Molecules don't know what their future holds. They just follow the lowest energy pathway. So since there's no energy difference of taking a secondary carbocation to another secondary carbocation, there's no reason for the initial shift to occur. So instead, in step 1 here, we have the same process for protonation of an alcohol. Protonation of the hydroxyl group in 4,5-dimethyl-2-hexanol, followed by the removal of a water molecule, gives a secondary carbocation. Since we can't undergo 2 hydride shifts, in efforts to make the carbocation more stable, we undergo the elimination of hydrogen to give a less substituted alkene, which you can see determines the placement of the double bond. And then here we see both of our major and minor products, and 4,5-dimethyl-2-hexene is yielded. So it is safe to say that in this instance, 4,5-dimethyl-3-hexanol will yield 2,3-dimethyl-2-hexene as a major product. Initially, in both cases, secondary carbocations are formed by the loss of water, but due to the hydride shift, the 1,2 hydride shift, in 4,5-dimethyl-3-hexanol, and assuming that 4,5-dimethyl-2-hexanol will not undergo 2 consecutive hydride shifts, 4,5-dimethyl-3-hexanol produces a tertiary carbocation, which is more stable and favored than a secondary, which was produced in 4,5-dimethyl-2-hexanol.